Welcome to our exploration of observational studies in epidemiology. Observational studies are research designs used in epidemiology where researchers observe and analyze health and disease patterns in populations without intervening. These studies come in various designs, each with specific purposes and methodologies. They form a critical part of epidemiologic research. Observational studies are crucial when experimental studies would be unethical, impractical, or impossible to conduct. They help us understand real-world disease patterns, risk factors, and public health interventions. Observational studies enable global health surveillance, helping researchers track disease patterns across populations and regions without disrupting natural processes. Even though observational studies don't involve interventions, they still require careful ethical considerations, including proper approval, informed consent, and data privacy. Observational studies can be contrasted with experimental studies. While experimental studies actively intervene to test hypotheses, observational studies examine natural occurrences without manipulation. To summarize, observational studies are vital research tools that allow scientists to observe health patterns without intervention, providing essential insights when experiments aren't possible or practical. Why do observational studies matter in epidemiology? Observational studies are crucial tools for understanding diseases and improving population health. They help researchers identify risk factors that make people more susceptible to diseases. These studies also reveal how diseases spread through communities, which is essential for developing prevention strategies. By assessing health outcomes, observational studies measure the impact of diseases and interventions over time. The knowledge gained from observational studies directly informs public health policies and interventions. For example, during the COVID-19 pandemic, observational studies identified that the virus was primarily transmitted through aerosols. This finding informed mask policies, social distancing guidelines, and ventilation recommendations. Ultimately, observational studies bridge the gap between scientific discovery and public health action, making them essential tools for improving population health. Let's examine the four main types of observational studies used in epidemiological research. These include cross-sectional studies, case control studies, cohort studies, and ecological studies. Cross-sectional studies provide a snapshot of a population at a single point in time, measuring both exposure and outcomes simultaneously. They're useful for estimating disease prevalence and generating hypotheses, though they cannot establish causality. Case control studies start with people who have a disease and a comparable group without the disease, then look back to assess past exposures. These studies are efficient for rare diseases or outbreaks, but may be susceptible to recall bias and selection bias. Cohort studies follow groups of individuals with different exposures over time to compare the incidence of health outcomes. These studies establish clear temporality and can calculate incidence rates, but they can be costly and time-consuming. Ecological studies examine relationships between exposures and outcomes at the population level rather than the individual level. These studies use readily available data and are quick to implement, but are prone to the ecological fallacy, where group-level associations may not apply to individuals. Let's compare these four study designs to understand when each is most appropriate. Each of these observational study designs has unique strengths and limitations that make them suitable for different research questions in epidemiology. Cross-sectional studies have several important applications in epidemiology and public health. These studies provide a snapshot of a population at a single point in time, which makes them ideal for certain research questions. One of the primary applications is estimating the prevalence of diseases or health conditions within a population. For example, cross-sectional studies are commonly used to assess health behaviors such as smoking rates across different populations. This graph shows smoking prevalence data collected through cross-sectional surveys, allowing researchers to track trends and compare rates between countries. Cross-sectional studies are also valuable for evaluating nutritional status within communities, identifying potential nutritional deficiencies or excesses. Researchers can collect and analyze demographic and health data from representative samples to understand nutritional patterns and inform interventions. Another important application is identifying health disparities across different demographic or geographic groups. Cross-sectional studies can also provide critical data for resource allocation decisions in healthcare systems. In practice, cross-sectional studies often examine both disease status and exposure factors simultaneously, as shown in this diagram. The key strength of cross-sectional studies is their ability to provide rapid assessments of population health status, making them valuable tools for public health planning and surveillance. Cross-sectional studies offer several key advantages in epidemiological research. These studies provide a snapshot of a population at a single point in time, making them much quicker to conduct than longitudinal studies. Cross-sectional studies have 6 major advantages. First, they're quick to conduct, often completed in weeks rather than the years required for cohort studies. Second, they're relatively inexpensive compared to other study designs, as they don't require lengthy follow-up or multiple data collection points. Third, they don't require participant follow-up, which eliminates issues with dropout rates and reduces logistical challenges. Fourth, researchers can study multiple outcomes simultaneously in the same population, maximizing research efficiency. Fifth, these studies are excellent for generating hypotheses that can then be tested using more rigorous study designs. And sixth, they're particularly useful for determining the prevalence of diseases or conditions in a population. When compared to other epidemiological study designs, cross-sectional studies offer distinct advantages in terms of resources and implementation. The difference between cross-sectional and longitudinal studies is particularly important. While longitudinal studies track changes over time, cross-sectional studies offer efficiency and immediate results. Cross-sectional studies have numerous real-world applications in public health. They're commonly used in national health surveys like NHANES and BRFSS to assess population health status. They're also essential for disease prevalence mapping, helping public health officials understand the distribution of conditions across different regions. Finally, cross-sectional data frequently informs public health policy planning by providing current snapshots of population health needs. Despite their utility, cross-sectional studies have significant limitations that researchers must consider. The first major disadvantage is the inability to establish temporality. Since both exposure and outcome are measured at the same point in time, it becomes impossible to determine which came first. This diagram shows how, in a cross-sectional study, we observe both exposed and unexposed cases simultaneously, making it difficult to determine if the exposure preceded the outcome. The second major limitation is the inability to establish causality. Cross-sectional studies can only show associations between variables, not cause and effect relationships. This image illustrates the difference between correlation and causation. Just because 2 factors appear related in a cross-sectional study doesn't mean one causes the other. The third significant limitation is survival bias. Cross-sectional studies only capture individuals who are present at the time of the study, potentially missing those who died or recovered earlier. This visualization demonstrates survival bias. The red figures represent cases that died or resolved before our study began. A cross-sectional study only captures the white figures, leading to potentially biased conclusions about the disease's severity or risk factors. When designing epidemiological research, it's crucial for researchers to account for these fundamental limitations of cross-sectional studies. Case control studies take a unique approach by working backwards in time. These studies identify individuals with a specific disease, called cases, and a comparable group without the disease, called controls. Unlike other study designs, case control studies start in the present and look back into the past. Researchers begin by identifying and grouping participants based on whether they have the disease cases or not, controls. Then researchers look back in time to assess past exposures, comparing the frequency of exposure between cases and controls. This retrospective approach makes case control studies particularly useful for investigating rare diseases or conditions with long latency periods. Case control studies offer several important advantages in epidemiological research. These studies compare individuals with a disease to those without it, looking backward to assess past exposures. Let's examine the key advantages of case control studies in epidemiology. First, they are highly efficient for studying rare diseases or outcomes. Second, case control studies require fewer subjects than cohort studies, making them more resource efficient. Third, case control studies are relatively quick to implement because data collection occurs at a single point in time. Finally, case control studies allow researchers to assess multiple exposures or risk factors for a single disease outcome. These advantages make case control studies particularly valuable for investigating rare diseases and exploring multiple risk factors efficiently. By leveraging these advantages, researchers can efficiently study diseases that might otherwise be difficult to investigate using other study designs. Case control studies have several important disadvantages to consider when choosing this study design. While case control studies are valuable for rare diseases and multiple exposures, they come with three major limitations. First, recall bias occurs when cases remember exposures differently than controls, typically because the disease experience makes them scrutinize their past more carefully. For example, mothers of babies with birth defects might recall prenatal infections more accurately than mothers of healthy babies, simply because they've been searching for explanations for their child's condition. Second, selection bias can occur when researchers have difficulty choosing appropriate controls that truly represent the population from which the cases came. This includes problems like non-response bias, where certain groups are less likely to participate, and Bergson's bias, where hospital-based controls may have different characteristics than the general population. The World Health Organization classifies bias into selection bias and information bias, with recall bias being a subtype of information bias. Finally, case control studies cannot directly calculate incidence rates because they start by selecting individuals based on their outcome status rather than following a defined population over time. Since researchers don't know the total population at risk, they cannot establish the true denominator needed to calculate incidence. Instead, they must rely on odds ratios rather than relative risk measures. Cohort studies can be divided into two major types based on when data collection begins. A prospective cohort study starts in the present and follows subjects forward in time. In contrast, a retrospective cohort study uses existing historical data to reconstruct and analyze a cohort. In both types, subjects are classified based on their exposure status and then followed to observe who develops the outcome of interest. The key difference is the timing and direction of data collection. Prospective studies move forward in time, collecting new data, while retrospective studies look backward, using previously collected data. Prospective studies follow subjects from the present into the future, while retrospective studies reconstruct cohorts from the past up to the present. For example, in studying diet and heart disease, a prospective approach would enroll healthy participants now and track their diets and heart health going forward, while a retrospective approach would use existing medical and dietary records to reconstruct past exposure patterns. Both approaches have their place in epidemiological research, with different strengths and limitations to consider when designing a cohort study. Ecological studies examine the relationship between exposures and outcomes at the group or population level, rather than at the individual level. These studies analyze data aggregated at the level of populations, communities, or geographical regions. Unlike other observational studies that focus on individuals, ecological studies look at entire populations as the unit of analysis. For example, researchers might compare obesity rates across different counties and correlate them with the number of fast food restaurants in each area. Common applications include comparing vaccination rates and disease outbreaks across countries, analyzing air pollution levels and respiratory diseases by city, studying GDP and life expectancy across nations, or examining smoking policies and lung cancer rates by state. Key characteristics of ecological studies include the use of aggregated data at the population level, inability to make direct inferences about individuals, reliance on existing data sources like census or health records, and their value in generating new hypotheses for future research. Understanding these population-level relationships can provide valuable insights for public health policy and intervention planning. While ecological studies provide valuable population-level insights, they have significant limitations researchers must consider. The first major disadvantage is the ecological fallacy. This occurs when researchers incorrectly assume that relationships observed at the group level necessarily apply to individuals within those groups. For example, a study might find that countries with higher coffee consumption have higher rates of heart disease. However, this doesn't mean individuals who drink more coffee have a higher risk of heart disease. A classic example is the correlation between ice cream sales and drowning deaths. At the population level, these rise together, but the relationship isn't causal. Instead, both increase during summer months. The second major disadvantage is the difficulty in controlling for confounding variables. Ecological studies only examine aggregated data, making it challenging to identify and adjust for factors that might influence both the exposure and outcome. Confounding variables can create misleading associations in ecological studies. Without individual-level data, researchers cannot adequately account for these factors, potentially leading to incorrect conclusions. Ecological studies have several other important limitations. They offer limited ability to establish temporality, cannot calculate individual risk measures, and are prone to various forms of aggregation bias. Like ecosystems have different trophic levels, epidemiologic research operates at different levels of analysis. Ecological studies provide insights at the population level, but are limited in their ability to draw conclusions about individuals. Understanding these limitations is crucial for properly interpreting ecological study results and designing comprehensive epidemiological research strategies. In epidemiology, understanding temporality and incidence is crucial for interpreting observational studies correctly. Temporality is a fundamental principle in establishing causation. It means that for an exposure to cause an outcome, the exposure must occur before the outcome. To understand temporality, let's visualize a timeline of events. In a proper causal relationship, the exposure must precede the outcome. For example, smoking, the exposure, comes before developing lung cancer, the outcome. When the outcome precedes the exposure, or if we can't establish which came first, we cannot validly infer causation. This is why temporality is a critical criterion in Bradford Hill's principles of causation. Now let's explore the concept of incidence in epidemiology. Incidence is the rate at which new cases of a disease occur in a population over a specific period of time. To understand incidence, consider a population of 50 people who are initially disease-free. Over a one-year period, 5 new cases of the disease develop. The incidence rate is calculated by dividing the number of new cases by the product of the population at risk and the time period. In our example, the incidence rate is 5 new cases divided by 50 people at risk over 1 year, which equals 0.1 or 10% per person year. It's important to distinguish incidence from prevalence. Incidence measures new cases over time, like water flowing into a bathtub. Prevalence measures all existing cases at a specific point in time, like the water level in the bathtub. Let's summarize the key points about temporality and incidence in observational studies. Temporality establishes the proper sequence of events, with exposure occurring before the outcome. This sequence is essential for valid causal inference in observational studies. Incidence measures the rate of new disease cases in a population over time and is crucial for understanding disease risk and the effectiveness of interventions. Understanding these fundamental concepts is essential for interpreting and evaluating observational studies. Prevalence is the proportion of a population with a specific disease or condition at a particular point in time. It's important to distinguish prevalence from incidence. While incidence measures new cases over time, Prevalence represents existing cases at a specific moment. We calculate prevalence by dividing the number of existing cases by the total population at that specific point in time. Bias refers to a systematic error in the design, conduct, or analysis of a study that produces results that differ from the true values. Unlike random error, bias is not reduced by increasing sample size and can significantly distort study findings. Common types of bias include selection bias, information bias, recall bias, and publication bias. Each type can affect different stages of research. Confounding occurs when a third variable is associated with both the exposure and outcome, distorting the true relationship between them. In this diagram, we can see how a confounding variable can influence both the exposure and outcome, creating a spurious association between them. A classic example is the relationship between coffee consumption and lung cancer. While coffee drinkers might show higher rates of lung cancer, this association could be confounded by smoking, which is linked to both coffee drinking and lung cancer. To summarize, understanding prevalence helps us measure disease burden, recognizing bias helps us evaluate study validity, and identifying confounding helps us interpret causal relationships correctly. These concepts are crucial for critically evaluating and interpreting observational studies in epidemiology. Choosing the right observational study design is critical to answer your research question effectively. Several key factors should guide your selection of study design, including your specific research question and objectives, available resources, time constraints, ethical considerations, and the accessibility of your study population. Each study design has its own strengths and weaknesses. Understanding these trade-offs is essential for making informed decisions. Cross-sectional studies are ideal for measuring prevalence and when quick results are needed. Case control studies work well for rare diseases and when resources are limited. Cohort studies are best for measuring incidence and require long-term funding. Ecological studies help identify population trends when only group-level data is available. To choose the right study design, follow a systematic decision framework. First, define your research question clearly. Second, assess your resource constraints. Third, consider ethical implications. Fourth, evaluate potential for bias. And fifth, consult with methodology experts when needed. As we conclude our exploration of observational studies, let's review how these research designs power public health insights. Cross-sectional studies provide snapshots of population health at a single point in time, ideal for prevalence estimates. Case control studies efficiently examine risk factors for rare diseases by working backward from outcomes to exposures. Cohort studies follow groups over time, establishing clear temporality between exposures and outcomes, while ecological studies analyze population-level data to identify broad patterns and generate hypotheses. These studies generate valuable real-world evidence that informs healthcare dashboards and policy decisions. To unlock the power of observational studies, it's crucial to select the right design for your specific research question. Consider your timeline and available resources, as some studies like cohorts require extensive follow-up periods. Evaluate whether your outcome is rare, which might make case control studies more appropriate. Assess if establishing a clear timeline between exposure and outcome is essential for your research, and determine whether individual-level data or population-level insights better serve your objectives. As epidemiology continues to evolve, new trends are emerging in how we collect and analyze observational data. By selecting the right observational study design, researchers can unlock powerful public health insights that improve lives around the world. Thanks for exploring observational studies in epidemiology.